Lab 7, gravimetric analysis of a metal carbonate. So in this lab, what we're looking to do is determine the unknown metal carbonate. So we have a metal carbonate. It's either going to be potassium carbonate or it's going to be sodium carbonate. Both of these are group 1 ions, and as we've talked about, these elements are so reactive they're already always found in salts bonded. So they're already bonded because they've already lost their valence electron. Okay, notice the carbonate ion is going to be that -2 ion. And a group 1 ion, whether it's going to be sodium or potassium, is going to be that M right there. So we're trying to figure out what our metal carbonate is. And at your lab stations, you're either going to have container 1 or container 2. And either one or the other has the sodium or the potassium. Please write that number down in your lab so that I can check for your accuracy. Now, what we're performing is a gravimetric analysis. That means we're going to be using specifically the mass. Now, I know gravity is more tied with weight, but we're going to be using certainly a mass analysis here. Now, how are we going to do that? Well, we're going to take our soluble metal carbonate. Now, why is it soluble? It's soluble because we know anytime you've got a group 1 ion, and we know something about Coulomb's law, we know in the crystal of this carbonate, we have the potassium or sodium ion is our +1 ion in the crystal, and we have our -2 polyatomic ion in our crystal. And I'm just making a very simple cubic structure here. It's probably not this simple, but I want all my students to understand it's a crystal lattice, and there are ionic type of bonds or attractions here that are very strong. And Coulomb's law speaks to the fact that this +1, okay, is probably not going to be large enough to attract this -1 in terms of how the water can pull these ions apart. So the negative part of water can compete with this attractive force of the carbonate because this attractive or this +1 charge isn't so great. I keep asking you to put this in terms of Coulomb's law, and what we know is that this force of attraction, electrostatic attraction, equals to some constant times the what? The opposing charge's magnitude over the distance squared. So if in fact this +1 is a small magnitude, that's a smaller force of attraction. Now in truth, these are relatively big ions, so you're stretching the distance too, but again, something to think about. So all group 1 ions are soluble, and so these sodium or potassium carbonates are soluble. They're going to dissolve in water and make what we call these free ions. Okay, so what are we doing here? Well, we're going to first dissolve this metal carbonate. And then the cool part here is that the carbonate that comes off from the metal carbonate, what we're going to do is precipitate out the carbonate using calcium chloride. So calcium chloride, a solution already made for you in a bottle at your lab table, is going to dissociate into the calcium +2 ions and also 2 chloride ions. These 2 chloride ions, as we know, are generally going to be also very soluble and do nothing in the reaction, just like our sodium and our potassium ions also are just going to essentially spectate throughout this entire process. Now, when we pour our dissolved metal carbonate, whether it's sodium or potassium, we're going to have these free ions in solution. We're not going to care really about the sodium or potassium, and that's kind of weird. The whole lab is about whether this is sodium or potassium, yet when we dissolve them, we're not going to care about these guys in solution. What we care about is this carbonate ion, and that's what the precipitation analysis is about. We know that there is one carbonate per 2 of these potassium or sodium ions, or there is 1 carbonate per every one of these formulas. That's important. So what we're going to do is that carbonate ion, we're going to add this solution of calcium chloride, which we know if it's aqueous, and it is, it's going to have these free ions in solution. And just like we talked about, the group 1 ions are always going to be soluble, and almost always the halogen ions are soluble. So those are going to basically spectate throughout this process. But the calcium plus 2 with a what? Large charge. Okay, and again, the carbonate ion, -2, a large magnitude of charge, is going to increase my force of attraction. So this calcium plus 2 is going to be attracted to the carbonate that came from our soluble metal carbonate to make a precipitate. And what we're going to do here is essentially take our free calcium ions that come from the dissociation of the calcium chloride. We're going to take our free carbonate ion that comes from the dissociation of this soluble metal carbonate, and they're going to come together and make our calcium carbonate. And again, you should understand why they make a solid. This plus 2 is a higher magnitude. This -2 is already big, so increasing your numerator is going to increase your whole expression, and the force of attraction in this case is going to be so strong that water cannot compete with it and cannot pull the ions out, and what you have is a precipitate. Now, big deal. So what? We're going to make a precipitate. But what do we know, party people? We know that for every 1 carbonate, there's 1 metal carbonate. Specifically, guess what? For every 1 carbonate, there's 1 calcium carbonate. For every 1 calcium carbonate, there's 1 what? Group 1 ion carbonate. These have essentially the same mole ratios. So when we precipitate out all of the carbonate ions, okay, what we're really doing is taking a piece of information along with the original salt. What's that piece of information? Every one of our metal carbonates has 1 carbonate. So what we're going to do is, if every one of these carbonates came from an original dissociation of the metal carbonate, we have a piece of information locked in our precipitate. And what is that piece of information? Every 1 carbonate is the same ratio as 1 calcium carbonate, which is the same ratio as 1 metal carbonate. So what can we do? Well, once we precipitate out the calcium carbonate, what we can do is we can mass it, and then we can convert it to what? Moles, which is our how many number. And if we know how much calcium carbonate, we know exactly how many metal carbonates we have. Hey, what we can do by massing out the precipitate and getting the moles of the precipitate, we can get the moles of the original compound. Now, what do we do with that? Well, we know that the formula mass, sometimes we'll write this as fancy M, pinky up, molecular mass, this is really a formula mass, but it's the same formula, is grams per mole. So all we have to do is, if we know the original grams of our salt, and we will, and if we can figure out the moles of our salt through the precipitate who has that information that we need with the right stoichiometric ratio, we can solve for the molecular mass, or in this case, the formula mass. And it'll give us the grams per mole. And you must say, well, how does that help us? Well, you should know what the formula mass of sodium carbonate is if you use your periodic table in the mole concept, or potassium carbonate. And you can see which one it is closest to. You certainly can also figure out the molecular mass of the individual M2, all right, as well, all right? So And you may say, well, how would I do that? Well, so another way we can do this is if molecular mass, really formula mass, I know, but if it's grams per mole, what we're going to know is we're going to know remember the formula is, let's say, M2CO3, that's the grams that we have. So the molecular mass could be there's two, of the individual metals that we have. So 2 times X, we're trying to find the mass of the element, plus the mass of the carbonate ion. We can do 3 times 16 plus 12 as we've done before. So the mass of the carbonate ion equals what? The grams that we're going to use initially for the mass of our metal carbonate before we dissolve it, over the moles that we get of the moles of the precipitate, which become the moles of the original salt through our stoichiometric relationship and our precipitation analysis. So what we're going to have here is we're going to have this value, and this value, and you can solve for the individual value as well. So it's another way to do that if you'd like. But essentially, very important you understand this process. We have, again, a very soluble what? We have a very soluble salt. We know that for every one of these carbonates, there's one of these formulas. And we know that when we drop the calcium ion onto it, the soluble calcium carbonate, we have one of these, and there's what? Every one of these carbonates hooks up with the calcium. So all of the carbonate ions that we precipitate out must have come from all of the what? All of the metal carbonate. So that's our link. And so we know the moles of the calcium carbonate. We know the moles of this. It's a 1-to-1 relationship because there's one carbonate per this formula and one carbonate per that formula. That's really important that you understand. All right, so that's the basis of this lab. It's a precipitation analysis. We call it a gravimetric analysis because we're using essentially the mass of our precipitate or our compound at the end to work our way back to what this compound is. Another form of an analytical type of lab trying to figure out what the chemical formula is. A little different from what we've been doing. So hope that helps. Get to it.